In this video we're going to define some notation which is useful for making some shorthand for expressions that come up very often in quantum mechanics. And this is called Dirac Notation, named after British physicist Paul Dirac, who was a Nobel Prize winner for his discoveries in quantum mechanics and other things. So let's define some terms here. We have the symbol here where we have a vertical line and then a number or letter and then a closing pointy bracket here. And this is going to represent this function fn of x. And usually what this will be the nth solution to the Schrödinger equation, the nth wave function for some physical system or some other analogous type of function. And if we have the reverse, where we have a pointy open bracket on the left and then a letter or number and then a vertical bracket on the right, this is going to represent the complex conjugate of that function. Then throwing these two together you see they kind of form this open and then closed bracket. They're this nice little bracket together. And this represents the integral from -infinity to infinity of fn star of x, our opening side on the left here, times fn of x, the function itself, integrated with respect to x, the closing side on the left here. And you can see this whole thing together, as I said, kind of forms this bracket. And physicists thought they were being clever, and they named this closing part here the ket, and they named this opening part the bra, so this bracket became a bra-ket. So you put a bra and a ket together and make a bracket, and that is bra-ket notation. And we're going to use this very often moving forward. So some other cases of bra-ket notation that come up a lot: if we have in general some function m and some function n, then this bracket mn is going to be, you can probably guess, the integral from -infinity to infinity of fm star of x times fn of x integrated with respect to x. Okay, that's nice and simple, no big mystery there. And then we can have m, some operator sandwiched in the middle between two vertical bars, n, equals integral -infinity to infinity fm star of x, complex conjugate of fm of x, and then the operator a acting on f of n of x dx. So just real quick, we can show how this can be useful in dramatically decreasing the amount of writing we have to do. In the earlier video about Hermitian operators, we showed that the condition for an operator to be Hermitian would be the integral of dx fm star of x a fn x, in the most general case, equals integral -infinity to infinity dx fn x, operator a acting on complex conjugate of the fm of x. Okay, so in Dirac notation, this shortens all the way down to m a n equals, and then all of this times its complex conjugate, or times taking the complex conjugate of this, we get 2 n a m star. So that's very much shorter. This complex conjugate, you complex conjugate n to get n. You complex conjugate from n star here to get n. Complex conjugate from a to get what should be there if I did this correctly, which is a star. And you complex conjugate m to get m star. So this Dirac notation is going to be a nice way to make integrals much easier and quicker to write, and will save you probably a lot of time on things like problem sets and other derivations.